Yeah, it's really my pleasure to talk a little bit about the various things that we're doing here at our laboratory, the European Severe Storms Laboratory. And I would like to start out with explaining a little bit who we are and how the laboratory actually started. So we are actually a non-profit organization and also an association. So that means we have members, and these members are weather services from various countries in Europe. Also EUMETSAT, the operator of meteorological satellites, the ECMWF, who makes medium-range forecasts for weather, and a number of research institutes, individual scientists, and also we have supporting members, and most of them are from the reinsurance sector. We were founded in 2006, so yeah, that's already quite a long time ago now. And we are a spin-off of the German Aerospace Center, DLR, that is located very close to Munich in southern Germany. The initiator of the ESSL was Dr. Nikolai Dotzek, who was a researcher at the German Aerospace Center. And he took the initiative to start the organization really after it became clear at the conference that he attended that there was well, not too much awareness of severe storms, and then I'm talking especially about severe convective storms, so thunderstorms in Europe, and that people were really saying like, well, we had this freak wind event in our country, it's never happened before, but it has this very long shaped area where all the trees have been blown down and there was big damage to houses. What could this be? Could it be a tornado? But tornadoes don't occur in Europe, do they? And there were a lot of such talks from people from various countries across Europe. And actually at that conference, it became very clear, like, yes, tornadoes are a thing in Europe. And the same thing was actually happening with regard to large hail, or even very large hail of 5 or even 10 centimeters in diameter. There wasn't too much of an awareness that this is really something that happens all across Europe, because if you look at one single country, then such an event isn't very frequent. But if you look at Europe, as we will see in a moment, it is actually quite a frequent event. So yeah, as ESSL, what we do is we do severe weather research in various types. We manage and maintain a database of severe weather observations, the ESWD, and we also organize and support the European conferences on severe storms. And the last conference we had was last year in Bucharest in Romania, and the next one will be in Utrecht in the Netherlands in November next year. There's also ESSL Science and Training, which is a daughter association located in Austria, in Wiener Neustadt, where we also have these premises that you see here on the left bottom. And this was founded a little bit later than the other ESSL. And what we do there is we organize a lot of training activities, workshops. We carry out the ESSL testbed and several research projects. And actually our employees and contributors are in various countries in Europe, really spread out a lot. Well, this slide is really full with all kinds of details, but it shows you the number of various events that we organize. So we have courses, we have these test beds that I will talk about a little bit more. We also have a number of workshops on various topics, including also tornado and wind damage rating. And recently we have been working a lot with EUMETSAT, the operator of European satellites, to get a better idea of some of the data that can help forecasters to better anticipate severe weather. And one of the things that the new instrument on the newest satellite, the third generation of Meteosat satellites, will be able to do is to get a better idea of low-level moisture, so the moisture in the lowest 1 or 2 kilometers in the atmosphere, which is crucial to understand if the atmospheric environment can sustain severe storms. Then at the ESSL testbed, so this is from the 2022 edition, where we had 5 different testbed weeks. We do this actually annually, or actually more or less continuously now that we work with all these satellite products. But as you can see, we work with many different products there. And the way that the testbed works is that we invite participants, typically from weather services across Europe, and we look at new tools to help forecasters to understand severe weather, or to make warnings and medium range predictions for severe weather. And yeah, something that we do is, for example, we compare various models, various atmospheric models that can predict the showers, and you can see here, and here is two model predictions of storms, and then on the right side you can see what the radar image really looked like in the end. And then we go and look into these products in detail, and we say which one was best and which kind of systematic errors we see. And in that way we really work together with the weather services, so with some of our members, to improve these various tools. There's also many other things. So, for example, here, crowdsourced reports. The German Weather Service has a collection of crowdsourced reports, or a way that users of their weather app can actually report severe weather. And then we're going to look into those reports and see whether they are actually useful for forecasters or not. Then for hail, as long as there's an image with it, we generally found it quite helpful. Yeah, there's also satellite-derived products, for example, of a flash flood that happened here in central Italy. But of course, a satellite can only see a storm from above, so it is usually inferior to radar. But then again, we can check this with the actual severe weather reports that happened on the ground, and we can see whether this was actually a useful product for the forecasters as well. And there's also certain algorithms that indicate areas where you have a chance that new storms will form. So it identifies from satellite-based or satellite-detected initiating clouds, whether storm initiation, so that they really produce rain, actually, yeah, whether that will actually occur, and with which of these storms that will happen. And we also have a number of other activities. As I said, we have courses on several topics. We also had a workshop on tornado and wind damage. Back in 2022, we had some webinars for Meteo Swiss, but we've also had a webinar for several of the ARPAs, the regional meteorological agencies in Italy. Yeah, and actually during the workshop on tornado and wind damage, we really went out and looked at the construction practices of new buildings, because of course we are not structural engineers, and we would really also like to have some insight into it as meteorologists, especially as severe weather experts. And at the testbed, we use the weather data displayer quite a lot, which is a highly interactive web page where we can actually look at vertical profiles of temperature and of dew point. And I just found that today it was quite nice what we could see on there. So I would briefly like to show you this, to make it a little bit like a current thing. Let's see, share my full screen. So actually this is from the newest satellite that can also detect lightning from space. And if I run this, we can see that there's actually, so let's go here. There's actually quite an active convective system here across Western Italy over the Tyrrhenian Sea, moving here into, I would say this is close to Naples already, which is extremely active in terms of lightning. So if we look here, it's really at the top of the scale, of the color scale here. So this must create a lot of lightning within these thunderstorm clouds. So these are things that we're also looking at. So how useful is this new lightning detection on the satellite compared to what we already had? Because there's also a lot of ground-based lightning detection systems. Okay, going back to my PowerPoint file. Let's see. So I will go through this quite quickly. Then I would like to present you, the main questions that actually drive us at ESSL. So you've seen we've been working on forecasting, but we also are more generally interested in finding out where and when severe storms occur in Europe. And of course, especially as the climate is changing and the temperatures are going up, does this have any influence on where and when severe convective storms happen? And what does it mean for the risk that these storms pose? And what are really the drivers of these changes in the atmosphere system? And then, as I already mentioned earlier, forecasting and nowcasting are important goals of us to improve forecasting and nowcasting. And very importantly, if you want to study severe weather, you of course first need to have some data on where do we know that severe weather occurs. So this map, for example, is shows our European severe weather database, where you can see all these symbols plotted on top of each other. Each of these symbols represent a reported tornado, reported severe wind gust, reported like large hail, or a reported extreme rainfall event. And it contains around 400,000 observations already. And there's quite a few requests, especially in recent years, for these data sets for people who will use it within their scientific studies or who like to use it to develop a risk model, especially those reinsurers and insurance companies that are really interested in that, of course. And as you can see, the severe weather in our database is actually increasing over time, but this is the number of reports. And of course, it's important to know that, we started somewhere here. So the point that it went up gradually after we started collecting those reports is not very surprising. And the question is, of course, does this also mean that there is a trend in the atmosphere? In reality, does the number of events also increase? And that's not so easy to answer. One of the things we also do at in the database is that we record, for example, for this severe weather event, we found that there were a lot of severe wind gusts, though those yellow symbols here, those yellow triangles, as a strong cold front passed here across Central Europe. But there were also tornadoes in this area in Poland. But besides recording that, we also recorded the type of impact. And you can see here all these greenish symbols over Germany actually stand for fallen trees. Whereas over the Netherlands and Belgium, there was much more roof damage. This is a data set that we haven't worked with that much, but we have, so I can't tell you why that is. I know that there are very few forests in the Netherlands and in Belgium, so maybe that's a reason why we don't see the tree damage. But why do we see so much more damage to structures? Maybe because there are more structures. Maybe the answer is simply that. You can also use the database to look actually at human impacts, so to check whether there are any fatalities or injuries caused by these various hazards. And this graphic here, this map, also shows some the categories for avalanches that we also collected. And of course, in the Alpine countries, this is really the dominating factor. So many people actually die in avalanches if you look at all the fatalities combined in this period. But there are, across many other areas in Central, Southern, and Southwestern Europe, flooding is really a big issue. But if you look at Eastern Europe, so Russia, Ukraine, Romania, Bulgaria, and also Turkey, there we can see that there are a lot of lightning fatalities. Probably this is because the agriculture in those countries really is not as mechanized, so there are many more people really outside on the fields rather than in tractors or in other machines, so that they are really exposed to the lightning much more than in Central and Western Europe. So financial losses, unfortunately, are not reliably recorded by the database because insurance companies don't really want to share that data. And originally, the sources for this data are usually from media reports or social media reports, and they are relayed to us by spotters in many countries. So we actually have agreements with clubs that call themselves, for example, Sky1 Poland or Sky1 Austria or the Amateur Meteorological Society of Czechia. And in Italy, we work together with Meteo Network and Pretemp, and they relay reports that they collect for their country to us. So we're very happy with this kind of collaboration with these enthusiasts. Yeah, this is what I already mentioned before. We have this increasing trend in reports, but yeah, there's a big question: what does that actually mean? Another thing, if you look at, for example, tornado reports, this is just some random period. You can see that there are certainly also issues with tornado reports that are hardly meteorological, because the atmosphere, of course, doesn't know where the border between Belgium and France is, for example. But we do see here, of course, many more tornadoes here on this side of that border compared to France, which probably has a lot to do with the reporting. If we look at it over a longer period in the recent past, we see that the number of tornadoes is more or less stable from year to year. Also, if we look at the various intensities, we see that, it is a bit of a stationary thing. So we don't see the strong increase in tornadoes that we see in many of the other hazards. Now, something very interesting actually occurred with hail, where we do see some trends that are so large that we doubt that this is just because of the reporting. If you look at where hail was reported in these years, and then we talk about hail of at least 2 or 5 or 8 centimeter in diameter, we can see that these last years have been extremely active, and 2023 was even more active year over northern Italy. I didn't have a newer version, unfortunately, of this graph. But to look more into the reasons for these changes, we carry out a number of projects. So, for example, the Convective Hazard Evolution under Climate Change project, and the researcher who is from Italy, Francesco Battaglioli, he just got his PhD last week on this research. What he has done is he has worked with a model. So he has developed a model to derive the probability of hail from information that you can get from weather models. So from models of the atmosphere, either forecasting models or also models that hindcast the past weather, so that give you the best representation of the atmosphere in the past. We call them reanalyses. And he developed a statistical method to get the probability of hail in this case out of that. And he did it by taking this problem in 2 steps, by looking at the probability that at a certain point in time and in space a storm would happen, so a thunderstorm, so there would be lightning, and also the chance that given that there is a storm, there's a certain probability of hail. So this conditional probability, and multiplying gives you the probability of hail. And to train this model, he used observed lightning data from ground-based networks, and he used the ERA 5 reanalysis, and also the reports from the European Severe Weather Database about when and where hail happened. And then you can look at 2 predictors. So in fact, he looked at many more, but for simplicity, we've shown 2 here. One that actually says something about the instability here on the horizontal axis. This is a form of CAPE, or actually it is the updraft speed that you would expect from a theoretical calculation by taking the amount of energy that is available to a storm. So what you do then is actually look if an air parcel goes up, and we know that in a convective storm, when an air parcel goes up, it accelerates further upward. And this acceleration you can integrate, you get an amount of work or an amount of energy that is released as such a parcel ascends to the tropopause, to the top of where these thunderstorm clouds typically spread out. And this amount of energy you can integrate, and then you can calculate the maximum updraft speed that you would get in meters per second here horizontally. And you can also look at the wind shear, which is another important ingredient for severe storms, because if you have strong wind shear, then these storms can interact with it in a sort of beneficial way, where the storms start to rotate, so the updrafts start to work in some kind of screwdriver motion, and actually the higher this energy and the higher the wind shear, the higher the probability of hail is. That is the theory. And in this case, this is also what we derived from the data that we had. So that was very nice. And then we can use a so-called generalized additive model to fit a function through these predictors. And we can also do that in more than 2 dimensions. And then if we reapply it to the reanalysis data set, so we do that both for hail, but we also have a similar model for the probability of lightning. We can actually get a distribution of hail across Europe. And we can do the exact same thing here across the United States. There is actually much more radar data available for the United States, and we can use that to see if we're actually seeing the same thing, if our model gives the same distribution of large hail as the radar detections do. Of course, there's also quite a bit of uncertainty in detecting hail by a radar, because if a radar sees some amount of the electromagnetic radiation that it sends out returned, that isn't a hail size, or specifically, there's quite a bit of uncertainty there in that estimate. But at least the distributions that we got from our model and from the radar were quite similar. Yeah, and in developing this model, this is a bit of a technical discussion, how we selected the predictors for that model. We wanted to use some form of energy, some form of wind shear, and then we also looked at a few other predictors that we could derive from that data set. And actually, it turns out that there's one parameter that is really important for hail that is between 2 and 5 centimeter, which is how high the 0 degree line is, because you could imagine that's somewhat smaller hail, or at least hail between 2 and 5, which is actually already quite big, that still some part of that hailstone would melt if the freezing level would be very high in the atmosphere. But for the very large hail model, that doesn't seem to be an important factor. And that came out of our model, and that also makes a lot of sense, because this very large hail has a much smaller surface area compared to its volume, so it won't melt as much in a relative sense. And these are then the the images that we get, the results from our model that tell you where hail larger than 2 centimeters and hail larger than 5 centimeters would occur in Europe. And also in Northern Africa, where we see very high values. And we have a bit of a problem to verify the very high values that we find there, because we don't get that many reports from that region. But occasionally we do get reports from extremely large hail from Algeria, from Tunisia. So we think the model may actually be right. Yeah, and I've shown the US as well earlier. And then, of course, an important question is that we can now answer is what happens if we look at this over a longer period. So we looked actually at a very long period from 1950 to 2022 to see if we to find out if we see any trends. And there it seems that there's actually a positive trend of this of these environments that support large hail from our model. And this trend is quite high, especially over northern Italy. And if we look at the extremely large hail, it's essentially the same picture. So it seems that the conditions that lead to these large hail events are actually increasing over time. And if we develop a sort of climate stripe visualization of that, they look like this. So we really see how recent years have much higher probability of large hail than in the past. And actually, for this very large hail, it is a 200% increase, so a tripling of the frequency of large hail compared, like in the last 10 years compared to the first decade that we looked at. And in the US, actually, the image is quite different. So there, actually, here we also have a part of Canada where there is a large region with an increase, and there's some increase here, but there are also large areas where we see a decrease. So it is interesting to look at this on a global scale and to actually see that that it is a very mixed image, and that Europe seems to be the area that is most at risk of an increasing large hail risk. Okay, and then we've also done this globally, and you can also see here on this animation what this distribution looks like globally. And some other hotspots that we know see a lot of large hail, for example, here in Argentina or in South Africa, they nicely show up here in this model. Now, if we go to very recent years, so now we enter the 2000s, have to have a look at Europe. So you see that Europe then will, especially these last few years, becomes more and more bright. So there we had an active year, there we had another one. And then 2022 was really off the scale. There was the most active region at all across the whole world. So that was a very, and 2023 was very similar, with again similar values there. We also had a look at if this change is maybe partly caused by different weather patterns setting in, but the quick result, the quick summary was that actually we found that these weather patterns, so the different flow patterns, have not changed too much, and to the extent that they have changed, they had very little effect in changing the probability of large hail. So most of the change is actually caused by local changes, or by changes that do not depend on the weather pattern that we see. And we found out that most of the changes are caused by an increase in this thunderstorm energy, this CAPE, which is becoming higher because there's more and more moisture in the lowest kilometer of the atmosphere. Which is, of course, not surprising that it has a big effect, especially across Italy and northern Italy, if we see increasing Mediterranean Sea surface temperatures, which is what we do see. So another application of this model is actually to use it for forecasting. So we have a forecast website, which is called stormforecast.eu, where you can currently see the forecast for today and tomorrow. And you can see also the hail reports that come into the database, so that you can get an impression of how good or bad the model actually is. And we're now working to make this work with ECMWF's large-scale ensemble of 51 member forecast. So that's 51 simulations of the future weather for the coming 10 days. And then we can actually have this type of product available 10 days ahead of time. So, and then I have a completely different topic, which is also something we worked on quite a lot. So I probably don't have the time to go into all the details of this, but I would like to show you the basics of this. So, and this is about assessing damage after a tornado or a severe wind event has occurred. And at ESSL, we've worked together with a number of people to develop this international Fujita scale. Yeah, this was very recently used after a tornado occurred on 24th of June 2021, a very big tornado in the southeastern Czech Republic. So Austria is right next to it, and Slovakia also. So this shows you that this is something that can very likely affect multiple countries. And in total, the length of this swath was 26 kilometers. And the highest damage that was registered in some of the central parts of this path was IF4. And I'm going to explain what that means. So there used to be wind speed scales. There used to be the wind speed scale that was originally developed by Ted Fujita back in the 1960s and 70s in the United States. And this has been the tornado damage scale that we've always been using at the ESWD. And it is all about comparing tornado events with each other by estimating the wind speed responsible for the damage. And there's a function that expresses exactly, if you have F so much, how many meters per second wind speed that corresponds to. And you can visualize it in this way, for example. But there are two problems with it, with this original scale. So the damage descriptions there were really general. And the wind speed to damage relation was not really backed up by science. And actually, in his later work, Fujita suggested to distinguish damage from weaker houses from stronger houses, which is, of course, very logical to do. So to really make it a bit more refined. So not saying that if a house is completely blown away, it is F5, but also considering that if it was a much more poorly constructed house, of course, maybe you don't need similar wind speeds. You don't need 120 meters per second of wind to get the same damage. Actually, we also made a first approach, but let's pause this for now. In 2007, then there was the enhanced Fujita scale, which is a scale that was initiated by a group of American meteorologists and engineers. And they made a much more extensive list of damage indicators, which was helpful to find out which wind speed was caused by a certain amount of damage. And it used the expert opinions of engineers and meteorologists to connect the wind speeds to the damage. But the new wind speeds were really different. As you can see here, they're really, really different compared to the original F speeds. And this caused a problem for us, because would we now have to re-rate all our tornadoes in our database? Because what we always thought was F1 should now be called EF0. Like part of these EF1 should now be EF0, or should we, what we used to call F5, would it be this or would it be this? It was very, very difficult to find out what this would mean for us in Europe. So yeah, and there was also a problem with this, another problem with this EF scale, that, for example, they said, well, if an elementary school is damaged to a certain degree, for example, the roof is lost, or maybe the whole building is gone, that then corresponds to so many meters per second of wind speed. as an estimate. But of course, elementary schools are not the same all around the world. So it sounded a little bit strange to use a building's function as the criterion to determine the wind damage speed with. So actually there were much more damage indicators needed, and we needed to have something that works more globally. And as this scale was introduced, there were also new variants in Japan, Canada, and France, which each had small changes to the original EF scale. So it became, I would call it, a big mess. So what we have tried to do is now to take a more uniform approach where we didn't have these changes here in the upper range or in the lower range. And we have now actually, and we actually looked at some measurement data, which were not yet available or very scarce when the EF scale was introduced, such as Doppler radar measurements, photogrammetric analyses. So for example, videos that show, for example, that some kind of object is traveling at wind speeds of 118 meters per second, which actually would correspond to the original F5. But then, of course, there's so that is actually the fastest wind speed measured by radar is actually 144 meters per second. So were these upper end corrections warranted that the EF scale people did? We actually don't know, because they're actually using a 3-second average wind speed, which is of course very common to use in engineering. But this is a quantity that is almost never measured in a tornado. Instead, we have these Doppler radar measurements. Sometimes we have photogrammetric analysis, and very rarely we also have anemometer data of the few. Yeah, but that's only, I actually know only of one case where there was really a wind meter that survived the tornado. And if you look at, for example, an image like this, you can see that in some tornadoes, the damage is really done in a time much shorter than 3 seconds, which is this averaging interval for wind speeds. So instead, we have decided to use the instantaneous and 3-dimensional wind speed at the height of the damage. And if we do that, and we use the original wind speed of the original Fujita scale, we get something that corresponds quite well to the wind speeds that are measured by Doppler radar, which are of course not instantaneous, but they are way shorter than 3-second averages. So together with some weather services, we came up with this wind speed range, and we took half steps for the lower end of the range, because we wanted to be able to indicate a little bit more precisely. And we said we are probably able to be a little bit more precise at these lower wind speed ranges. And this is once again to show that actually the measurements going up to this red dot here are actually the radar-derived maximum wind speeds in tornadoes by the mobile radars operated in the United States, who measured a lot of tornadoes. So we have first applied this to this tornado in the Czech Republic, even before we introduced this new international Fujita scale. And we also improved the scale, or at least we hope this is an improvement, that we used more generic damage indicators. So instead of saying it's an elementary school, or it is a shopping mall, or it is an outbuilding, we gave some descriptions, and they're more detailed, and they should be even more detailed than they are now in the current version of the IF scale standard. That we gave more detailed descriptions of these houses, where we really distinguish the sturdiness of one particular building to another building, and not relate the sturdiness of a building directly to its function. So there's a lot of different objects that can be damaged to a certain extent. So there can be several degrees of damage to several so-called damage indicators, and each combination of a certain damage indicator, and a degree of damage will result in a certain IF scale rating. We also have developed an app which is actually available for testing, and yeah, the IF scale document is also available now. And we have in the meantime published that. So this is another completely different topic that we were also active on as ESSL. And now I would like to conclude by going quickly through yet another topic that we're active on. I will try to stay within the time. I think I have about 5 minutes left. So this is the European Meteorological Field Campaign on Severe Storms, called TIM. And TIM stands for Thunderstorm Intensification from Mountains to Plains. We would like to understand extreme thunderstorms better in order to give better warnings and improve meteorological models, to understand the mechanisms between mountains, the adjacent plains, and severe thunderstorms, and also do research on extreme flash floods and hail. So there's this question also, why do we see this huge increase in hail in the vicinity of the Alps? Low-level moisture is probably part of the story, but there's a lot of understanding missing related to actually what contributes to the hail. If we have for example, if we have an idealized model of a thunderstorm cloud and we increase the energy that is available to that storm, the idealized model doesn't show that the hail size increases a lot. Actually, it shows that the smaller hailstones that enter a thunderstorm updraft are spit out by it, to summarize it very, very concisely, and that the large hailstones are less likely to form. But in reality, we actually see that the number of hailstorms is actually increasing quite a lot. So that's a question that we can answer by having much more data about what is happening in those thunderstorms and surrounding those thunderstorms. For example, we also have questions on how to understand why these storms are always so severe next to the mountain ranges. Well, we have some ideas, and there's quite a bit of knowledge of why these storms occur on these slopes, why they start to develop on the slopes of the Alps, for example. But we don't know why they are so severe as they typically are. And there are some theories that we would like to test. For example, is it that the upslope flow towards these mountains, contrasting with the flow at higher altitudes in the opposite direction, creates a lot of wind shear that somehow increases the intensity of these thunderstorms? That is a question we would really like to answer, not only by modeling this, but also by measuring what is really going on. Because if we use models, we see that these models are not always right. Sometimes they have a rather good simulation of storms that develop during the course of a day, but there are also cases where the models completely fail to develop the models, or that a model says that the thunderstorm will develop into a squall line, so a linear type of convective system, rather than an isolated rotating supercell that produces hail. So instead of forecasting a hail, it would then suggest that you would get wind, which is pretty common with such a squall line. So to finish this presentation, we are working this year a lot on fundraising, on getting financing for this project. We also are still looking for more partners that we would like to work with. We already have many of the weather services on board. They want to support the campaign with their own means and by sharing the data that they already collect by the measurement networks that they operate, including radars and ground-based sensors. And there should, of course, be several teams within the project that work on different aspects of it. And here's just an overview of the various the various types of instruments that we want to use. And actually the drones are missing. Oh no, here they are, the unmanned aerial vehicles. So that's an important thing. We think we can get a lot of new data from the drones. And there are also new types of sondes that can be released first from a balloon. And then actually, if you release it, they will move through the storm and measure very precisely what is going on there in terms of temperature, humidity, and pressure as well. So here's a number of partners that are already on board with the campaign. And yes, and of course, my colleagues and I, we would be happy to hear about other people who are interesting new partners that we can find. So with that, I hope I've given some kind of more or less complete overview of my presentation or of the activities of the European Severe Storms Laboratory. Of course, I couldn't say everything, but I think I talked about a lot of stuff, and I'd be happy to answer some questions about particular parts that you would like to know more about.